what is projectile motion? Projectile motion anytime something's in the air and the only acceleration that's acting on it is the one due to gravity. Only acceleration is due to gravity. Which means it's g, or negative 9.8 meters per second squared down. So it's basically two-dimensional free fall. And just like free fall, it doesn't mean you have to be traveling down. You can be traveling up or, in a variety of ways. So for example, maybe you're on a cliff and you kick off a stone or a ball or something, and it's got some initial velocity and it travels up, and then it falls down and hits the ground over here, somewhere down away from the cliff. And maybe, let's see, what else might you know? You might know the angle from the horizontal that you fired it off at. You might know how tall the cliff is, we'll call it h. You might know how far away whatever the object was fell, we'll call that distance L for the length away. You'd also know, for example, that the up and down component of the velocity is 0 right here at the peak, just as in free fall. When you're going up, you're slowing down in your upwards velocity, and then you have to stop momentarily before you can turn and come down. The same thing is happening here with just the vertical component. The horizontal component, of course, you can keep moving. So we've got this set up. In order to say what we need to say about it, we're going to have to put some axes on. So looking at this, I can see I've got horizontal information here, how far away I've landed, vertical information here. So despite the fact that my velocity isn't horizontal or vertical, it has components of both, I'm going to choose So looking at this, I've got horizontal information here, the distance away from the cliff we land, vertical information here. So despite the fact that my initial velocity isn't horizontal or vertical, it's got components of both, I'm going to go with these two and choose an axis system which is horizontal and vertical. And I'm going to call the horizontal bit x, and I'm going to call the vertical bit y, and say up and to the right are the positive directions. Now, having done that, I can start writing down what I know. And I can divvy it up into horizontal and vertical pieces of information. So for example, I might know where I start, I might know where I land, my landing position, y sub L, So looking at what I've got set up here, I have some horizontal information going on, kind of where I started to where I land. I've got some vertical information going on. So despite the fact that my initial velocity isn't really horizontal or vertical, it's got components of both, I'm going to choose to go with these two bits of information to make my axis system. I'm going to choose an axis that is horizontal and vertical. And I'll make y my vertical stuff, and I'll make x my horizontal stuff. And now that I've got that axis system, I'm going to divvy up the information. So I'll have vertical information, the up down stuff, and I'll have horizontal information. And the vertical information is going to be the y stuff, and the horizontal stuff I'll call x. So vertically, what might I know? I might know the initial position, I might know the landing position, maybe I know the position at the top. My top there, y land there, y initial there. I might know, given that I've got a v naught and an angle here, I might know the initial y component of the velocity, or maybe the y components of velocity to any of these places. And I might also know, in fact I do know, the y acceleration. It's going to be g, this negative, or this 9.8 meters per second squared. And in fact I even know that it's going to be negative g, given how I've done my axis system. I've set up as positive, and that means g, which is down, is going to be negative. And I'm just going to go ahead and write in here. I would know that y vertical, well, I need a triangle to do that. What else could I say? Oh, I did say that the y component of the velocity at the top, so the top, the y piece, that's going to be 0. And maybe I know something about the landing velocity, but maybe not. Horizontally, well, I might know the initial horizontal position. I might know the horizontal position where I am when I land. That's L, in fact. I might know the initial horizontal component of velocity. Same triangle would give me those. And I also know the horizontal component of acceleration. It's vertical. The horizontal component of acceleration is 0. And that actually means if I know the horizontal component of velocity at the beginning, I know it all the way through. I know it when it's at the top. I know it when it lands. I just know it the whole time because acceleration in the x direction is 0. That means the velocity doesn't change at all. All right, so let's put in information that I know here. So that, I'm going to write it in purple because it's based on my, the axis system I'm doing here and what I've written down in the problem. So my x distance away is xl, where I have landed, x equal to L. My initial x position, well, it's here. It's at 0 on the x-axis, so that would be 0 here. My initial y position, well, if this is 0 in y, I start up the distance h above that, and it's also positive, because I can see upward is a positive direction. I'm above the origin. Let's just go ahead and write in explicitly. That's the origin right there. That's the place where y is equal to 0 and where x is equal to 0. Let's see, where I land, that looks like that's it, y equals 0. Yeah, I don't really know this one. I haven't given myself information, so we'll leave that open. Now let's figure out these components of velocity. So I'm going to redraw this triangle down here, so I just got a little bit more room. That's the angle to the horizontal, theta. And to make the right angle, well, let's see, we want to drop this down right there. Then we've got our right triangle. And something to notice is the right triangle is always, the right angle is always opposite the actual full velocity vector, because the magnitude of the velocity vector, when you're dividing a vector up into components, that magnitude is always the hypotenuse. And then if we do that, this here is going to be the x component of velocity, and this here is going to be the y component of that initial velocity. And again, we're dividing up into components, so we've always got to get the magnitude, and then we just got to figure out which trig function we need. So let's see, this side here that is x is adjacent to the angle, so that means this is going to be cosine of that angle, and this side here, that's opposite the angle, so it's going to be the magnitude times the sine function. Okay, and that tells us what we need. So that says my x velocity is going to be v naught times cosine of that angle all the way through. And at least at the beginning, my y velocity is going to be v naught sine theta. But then, of course, that one's going to change because it's the y component that's got that acceleration. All right, so what else can we do here? Well, there's one other thing that we know. We know it's probably, we're going to start the clock here. So t will be equal to 0 here, and then this will be however long it takes to get to the landing time. And t will be shared between the two. So you'll have t to the landing time is whatever it is in x, but of course it's got to be the same thing in y. Because when you arrive here at the landing spot, you have to get there in y, up and down, and x at the same time. So here, say we want to figure out what's going on at this landing spot, we can solve for time in x, say, and then use it in y. So let's set up the equation we might use to do that. So here we know we have a constant velocity, so that means that the average velocity is equal to the instantaneous velocity anywhere. So we can go ahead and write horizontally, the velocity is equal to the distance we've traveled. So say the landing spot from the starting spot is what we're interested in, over the time it took us to get there. So the landing time minus the initial time, but of course the initial time is 0. And it turns out we've chosen, in this case, we've chosen the origin to be where we start in x. So for this particular coordinate system, I can write that the landing distance over the landing time will give us the velocity in x. And then I can rearrange this. I'll multiply by the landing time on both sides. I'll divide both times by the initial component of the x velocity, and I'll get the landing time is equal to the landing position in x divided by the initial x velocity. And we can even plug in what we know about that. We get the landing distance, and then the x velocity is v naught cosine theta. And that information I've just got from right here. That's always the horizontal component of the velocity. So now that I have t, I've solved for t, I can plug this back in here. Because, again, time is shared between the two. If this is how long it takes us to get to the landing spot in x, it's also going to be how long it takes us to get to the landing spot in y. So then I can add t to my list of known things that I have on what's going on vertically and solve for any of the other things I need to do. And that tends to be the main trick with projectile motion information. You find one direction, either horizontal or vertical, or other axis systems if you want, but usually horizontal and vertical, because that divvies our acceleration up into constant and 0, which, again, another constant, but a constant which makes our life really easy in the equation. So you'll divvy them up like that, and you use one direction to find time, and then you can plug that time in to the other direction to solve for things. Sometimes it'll be easier to solve for time in the vertical direction. Say, like if you're at the top, where you know something about the velocity, you know the y component, the vertical component of the velocity is 0 at the top. So maybe then you'd solve for time up here vertically, and then you can plug time down here into the horizontal information. So that's pretty much what you need to know about a projectile motion problem.